We discussed the binomial distribution. There is also the Poisson distribution. I say they give essentially the same answers. The Poisson is effectively the continuous limit of a binomial distribution, where you have a time interval dt. That's effectively a time interval where you do at least a virtual tossing. Then you have a probability lambda dt of something happening in that time interval. That lambda dt is effectively your mu in the binomial distribution. Lambda dt is always small, and you can then calculate what this Poisson distribution gives. It's the simplest example of a Poisson distribution is nuclear decay, because there Mother Nature will generate decays with a certain probability, which ensures that the chance of a decay happening in time dt is indeed lambda dt. And you can go again to Wikipedia and find out exactly what's going on, and you will find that for a Poisson, always the mean is the square of the standard deviation. So it again has the square root law. This plot here compares Poisson, which are the black lines, let's like this, with various binomial distributions. And when you have when you do the things finely enough and chop the binomial up into many small steps, you will find the binomial looks very similar to the Poisson. And even for modest sized binomial, and you take your case and you divide it into 10 tosses, still the binomial is not so different from the Poisson distribution. Wikipedia in this article on the Poisson distribution gives lots of examples. There's one obvious. One example is cars arriving at parking lots, telephone calls arriving at an exchange, photons arriving at a telescope, um, and so on. Cars arriving at traffic lights. Actually, parking lots are an example of a more general concept, because cars not only arrive but they leave. So that's called a birth and death process. The birth is the cars arriving, and the death is the cars leaving. And they might have have probabilities which are some constant times dt with possibly different values for that constant. Another important example of birth and death processes occurs in population dynamics. If you have a collection of fish and sharks, maybe the fish give birth with a certain Poisson distribution. They get eaten by sharks. That's a death process, so that corresponds to the fish disappearing rather than appearing as they do when they're born. And birth and death processes all have these probabilities that are linear in time, but so they can either have positive or negative impact on the number of entities there. And you can calculate several, when you go to the literature, you'll find several examples of multiple species with different interactions of each species on another species, and solving the coupled differential equations. Here's yet more examples. Number of soldiers killed by horse kicks is claimed to be one of the earliest cases where this was studied. Number of cells used in brewing beer was seems as important. Deaths per year in a given age group. So stock market has Poisson distributions. Number of times a server's accessed per minute, and so on. So there are many examples of Poisson